Dr. Anindita Datta is an environmental health scientist whose research focuses on understanding the impacts of ambient and household air pollution on maternal child health, other diseases like hypertension, cardiovascular, diabetes, reproductive health, and on adverse pregnancy outcomes. She's been working in Asia, North America, Africa for over 18 years, leading research on air pollution and public health, and has led collaborative research partnerships with various academics, community partners, and government agencies. I would now welcome her to take forward this session.
Good morning, everyone. I'm Anindita, and I'll be moderating today's CAMS-Net session towards clean air for all, improving, measuring air pollution in your neighborhood. In addition to what Anshika already introduced about me, so I really don't have any institutional affiliation right now in between jobs, but I do serve as an editorial board member on PLOS One and BMC Public Health. And I'm also an executive committee member of Environmental Health Language Collaborative, which is an NIEHS initiative in the US. And we have a poster put on there, so please see that. And there's a scan code, a QR code, which you can scan and know more about this initiative and how to participate. I'll just start with sharing an anecdote that I already did on my LinkedIn profile, and many of you who are here reacted to that. So last week, I was in Mumbai. Specifically, we were talking about Friday because the rain started since Friday night, so the air quality was really good on Saturday and Sunday. So I had my phone, which, I mean, this is in context to like why measuring air pollution at your neighborhood level is important. So on my phone, the whole day, the AQI was sometimes 34, sometimes 67. I particularly remember these two values because when I was stuck at a traffic junction in Dadar, the air quality was showing 34. And if you roll down the window, you really can't breathe it. While I was going by Marine Drive, which is much cleaner, and you could essentially like smell or breathe fresh air, the air quality, the AQI at that point of time was showing 67. So this doesn't really correlate with what I'm experiencing and what is showing it over there, right, on my phone. And that's where it's very necessary that we need to, measure air quality level at the neighborhoods, at our neighborhoods. So we have 4 amazing scientists. 3 of them are in person here. 1 will be joining virtually, who will be presenting their research on this topic. And the housekeeping rules, in essence of time, since we started about 10 minutes late. Yeah. So we will not take questions after each talk, but we'll keep the floor open for questions once all the 4 talks are over. Our first speaker is Dr. Soumya Singh. She is an assistant professor at the Indian Institute of Forest Management in Bhopal. Earlier, she was a research scientist at the University of California, Berkeley. She earned her PhD in environmental sciences from JNU and completed her postdoctoral fellowship at the University of Toronto in Canada. She has many achievements, but one of her most notable work that I thought that I should mention over here is she has led the Samosa sensor network. It's quite kind of catchy term, Samosa, in India to explore the rural-urban air quality linkage. So over to you, Soumya.
Thank you for the introduction. Good morning, everyone. My name is Soumya Singh. My introduction is already done, I'll just start with my presentation. So I was putting together, I had all the slides ready, and it's been more than 3 years I have been working on this, 4 years actually. So I was thinking that, for the theme, how do I actually make the story? Because, I have the analysis, tons of analysis done. But then the story, whatever the conclusion from the talk I have, it's already very much aligning with the session. So we did measurements. So from the samosa, most of you might be knowing about the campaign. So basically it stands for, I also have to think, samosa. So Sensor Air Measurement Observatory in South Asia. So we started with a very much, like an ambitious goal of having a measurement across South Asia. So the talk today will be most of, the measurement we have done in India and also very much focused in North India. So I would like to start, with the acknowledgement of our collaborative team. So from the UC Berkeley, we have Maria here, and then IIT Delhi team, we have Sophia here. So if you have any additional question later after my talk, you can also chat with them. Also, we have Arithmetry is at the end, but very special, collaborator, Gautam is also here, who really helped us with the data, data management, and also open philanthropy for funding the project. So I think by now we all know and you understand that the Indo-Gangetic Plain is experienced severe air pollution, and the goal for this project, so that's why I'm focusing on rural, rural area, because most of the population, so more than 65% of the population actually lives in villages in these areas, but we have 4 years before when we started, we had a limited measurements, and I think if we think about, if we talk about the current status, it still exists that, the rural measurements we don't have the measurements in this area still. So the motivation was to understand these, rural to urban gradient. And what you see here, the India map, and then also the graph is actually, it's not our research, it's, published by Ravi Shankar et al. In 2020. It's basically what it's showing is the population weighted PM 2.5 and on a y-axis. And what you see here on the x-axis is they have divided the entire country in different regions. So that's North India, IGP, Eastern India, Western India, Central India, and Southern. So if you see that, the difference between the urban and non-urban, it's not very, it's not that big of the difference. So both urban and non-urban regions are very much comparable. So these are basically the satellite-based measurement and the model-based study. So the Samosa goal was to understand the rural and urban linkage in this area. So I'll talk about our study framework, how did we design this. So what we did, we actually divided the entire IGP in several clusters. So cluster here is just a meaning of geographical, clustering the geographical settlements, not something with the statistical meaning. And in a one cluster, so we have, for example, 4 or 5 clusters. So in one cluster, what we did, we have a settlements. So settlement would be large city. Those are based on the population. And large city, then a small city, then town, then villages, and background. And large city we kept as an anchor settlement. Then what we have is, in each settlement, we will have a multiple sites just to cover all the land uses and sources with the limitation of the census we have. Then, all right, so as I mentioned already, so you can see this is basically IGP, and these are the satellite estimate of PM 2.5, and that's how, these are the blue circles you see, not perfect circles. These are the clusters we wanted to target. So I'll be talking about one of the cluster result here. Okay, so the cluster design, why did we select these clusters? These are basically based on the, if you attended Sarath's training, and if you are familiar with the urban emission, he has come up with the latest, 15 airshed reasons which we should focus on in India for the air quality management. So basically, we had some results from the Sangnik Day group. So we actually overlaid our design, and then we found that, okay, we are covering these airshed reasons. So, these are also based, our study is also based on the population estimates and also the airshed approach. But I'll be talking about just one or two clusters actually. So then once we went to a settlement, for example, a city, how do we choose our sites? So our site selection is basically like, the different land use I was talking about yesterday also. So, we will map the tree cover, residential site, the industrial site, residential traffic site, and then other, land use, other sources area. And then what we do is we overlap. So it's not the perfect way to do it, I guess, but we were doing it 4 years back. So now when I see there are other maybe more advanced way to look at the site selection, but this is what we did. And so once we had this, just a second. Once we had these sites, we will go with our already co-located sensors and deploy these sensors. So we, throughout the study and the presentation, I'll be talking about 4 settlements, so large city, small city, town, and villages. And I just put this slide today only just to let everyone know that, because when I present, I forgot to mention what sensor I'm using. So I have used Purple Air, and that time, I think it's the global network I have taken this snapshot is actually 3 years before. So it's definitely more than this, we have the sensors. Okay, so this is the cluster I will be basically talking about, and we had around 80 sensors in these 2 clusters. And so on the right side, when you see the large city, basically those are mix of one sensors deployed by us and also the regulatory monitors. The stars will be regulatory monitors. But in villages, we do not have a regulatory monitor, so that's just our deployment. All right, we had enough discussion on the robust, the protocol about the QA/QC, and so I'll just quickly touch upon what we did. So for our study, we actually took sensors. So when we got from the US the Purple Air sensor, we actually co-located that with the BAM, and we had a three co-location site. So we co-located that with BAM, and then that's the mass co-location. First, we actually see the precision between the intra-unit, so basically between the different Purple Air sensors we have, and then we actually compare that with the BAM. So I think for calibration and co-location, we all understand the process. So for after 2 or 3 weeks, we will actually assess the performance, and then we will select the sensor, and then we will send that to field. But then we will also keep 2 sensors from that batch for a long-term evaluation, just covering the entire season. And then in the field, for the field deployed sensor, we will be checking our sensor every day. We had a really amazing team, so it's a big team. So just a quick daily checks on QA/QC, and then we will develop the weekly QA/QC protocol. So we will just go through different metrics for the sensor performance, and then we will evaluate the QA/QC. So the metrics we use are R-squared, slope deviation, and uptime. All right, so we had actually this project journey started from CSTEP only, although the data is not, because it's in Bangalore, and we did not take this for the calibration, but interestingly, the first co-location happened at CSTEP only, and that's me actually 4 years back, hanging all the sensors. And then we had one co-location center site at a rural area in IGP, that's called IGP Care Hamirpur, and then we also have one co-location site at IIT Delhi. So we tried to minimize the sensor-to-sensor variability and really wanted to develop long-term seasonally resolved calibration. And if you're interested in knowing about our calibration model and co-location scheme, we have this paper already published by Mark Campier et al. In AMT, so please have a look if you're really interested. So, so for the calibration, the data I'm going to present, we use the multilinear regression model for that, and this is the equation. And I think for these relatively simple model, actually, for us, at least in our study, it greatly reduces systematic bias and error. And you can see R-square was 0.94 and 0.22. So we had 3 stations like Bangalore and then IIT Delhi and Hamirpur, but the Hamirpur model actually worked best for our data for the cluster. Okay. So this is again like more from the calibration, that how our raw data was actually when we compared with the reference grade, and then when we corrected that. So if you look at, what is this? I don't know. Okay, now. Okay. So these are basically the, yeah, so these are basically the hour of the day variation. The first one, the graph, and then the bottom one is basically the month of the year. So this is, when we correct, you can see the normalized residuals are very much close to the zero line, but it's like 20% definitely. I can see more than, it's around that zero line, but the raw data, I mean, that's basically, this is showing the, how our data actually got improved after our calibration model developed. So just to give you some insight, some glimpse, how far we went. So these are the, field sites. We went to rural area, and so in a village, we will actually go to a residential place, and then also we will try to cover the farms also. So this is one of the example we have. This is also one of our field assistant putting the sensors, and these are smaller cities. So some smaller city, not Delhi. Yes, okay. So then I'll start with the most important thing about the data availability we have been talking about. So these are on x-axis, you see these are site ID, and we had 80 sites that time when we started. And these are 1 year of the data. On y-axis, you see basically 1 year of the time period. And whenever these are color-coded with the settlement type, so red is, the brown is the major city, yellow is the small city, and then green, light green is the town, and dark green is the village. And whenever you see white space, and that's basically the data gap we have. So just to give you more clarity about this, I actually arranged this based on, so now you see the first, really? Okay, sorry. So the first is the brown, and then yellow is, so what I really want to highlight here is that we had really good coverage in villages also. So that's our achievement from the study. All right, so if we come to the results, this is, I have been presenting this for some time, so maybe some of you already know this, but then, this is a 1 year of data. The first graph is showing the time series, so 2-week, bi-weekly moving average. So it's the time series data, and then on the right side, you see these are basically the settlement type-wise averaged for the season. So, the most interesting part about even if you don't go into the details, it's like all the settlement type, rural area, villages had the same level of PM 2.5 pollution as we have the neighboring cities. And the seasonality we see, we have better understanding from the beginning, from other studies as well. Now, when we look at the diurnal based on the season, we also see, the similar patterns for all the settlement types, except those sharp peaks during the post-monsoon winter and also summertime. And especially those smaller settlements like town and villages showing the sharper peaks. So that, the similar pattern is showing basically we have a regional sources for all the settlements in that one cluster. But then the sharper peaks probably is showing the local sources we are getting from cooking or biomass burning from that area. All right. So, we wanted to also understand what is the inter-settlement if we have 7 sites within a city or 4 sites within a village. What are the differences we are seeing? So what I did, I actually took the few weeks of the data where we have the 50% time of the availability of the data. So these are, like 47 sites. We started with 80 sites, and now for this analysis, we are left with the 47 sites. And then when we look at this, so what this graph is basically showing is on y-axis PM 2.5. So basically that one bar is showing the distribution of the large city sites. And then these light color, actually brown color dots are showing so we had 3 large city. So you will see 3 lighter brown color, and then that dark color is basically the average of, grand average of that large city. So you can see that we started with all the settlements have a similar pollution level. But then when we really look at the different villages and different city, when we go into the inter-settlement level, we do see the differences, like coming from somewhere from 80 microgram per meter cube average to the 120 or 130 microgram per meter cube. And the spread for the villages we have seen was larger than the city we observed. And then these are basically showing again on y-axis, x-axis you see the settlements, different settlement, and then the dots are showing the site average for the PM 2.5 for those different sites basically. So you can see all the sites from the different settlement are more than always 50 microgram per meter cube, and sometimes going, one of the site from town we observe as always showing the average more than 150. But that particular site was having influence from the biomass burning very close by. So I think I can skip this one because we wanted to explore what are the background and peak concentrations. So this is just one example of one settlement. We actually tried to, okay, so I'll skip this, but we can chat later about this. Also, we looked at the correlation between different sites and settlement, and these are always we found that the Pearson correlation coefficient was more than 0.7, so largely telling about the regional contribution of the and then just to just to confirm if what we are seeing in these settlements are very much similar sources. So we also looked at the backward air mass trajectory for 3 settlements, and when we divided that, we had 4 clusters, major cluster, and all trajectory were showing similar, contribution direction for the air mass trajectory. All right, I can skip. I will be happy to chat. So this is the summary point. Very largely, I wanted to keep this. So smaller settlements, as we were talking about the neighborhood measurement. So if we do not go and measure, we would not understand whether we have also, pollution at villages level. And these diurnal variability, we see that, we understand the regional influences are there, but also there are local signals coming from the burning air, morning and evening. But the most important point I actually want to highlight here, that to support a large network, we worked very hard for 4 and still this campaign is going on. And having a great team and focusing on standardizing and scalable procedure is much more important. So I think I will end with that. And this is me, the left one, starting at CSTEP, and then with this, and also we have team members. So yeah, thank you. And there's some pictures showing that how we were doing co-location and yeah. So thank you so much.
Thanks, Soumya. Before I move to the next speaker, Garima, I just wanted to say how excited I was to see, my hometown is Bandel. And today morning in Subbu's slide, I saw that map which he took from Faye's work. So it was really exciting. And I really want to take this opportunity to thank Dr. Kalyan Rudra, Namaskar sir, who is the chairman of West Bengal Pollution Control Board. And thank you, sir, for understanding that how important and how necessary the measuring air pollution level at the neighborhood levels is. And thanks to Faye, because I still have one low-cost sensor, the purple air monitor, which is still running at my home in Bandel. And I would also take the opportunity to thank Dr. Debashish Chakraborty, who is the Chief Scientist of West Bengal Pollution Control Board. Namaskar, sir. Thank you for this ongoing collaboration with Faye, who is also, what do I say, Bouma of West Bengal, daughter-in-law of West Bengal. So it's really nice. Anyways, so moving on to our next speaker, Ms. Garima Raheja. She is a PhD candidate at Columbia University in New York City, where she researches air pollution and its impacts on urban communities around the world. Garima serves as a US Department of State Air Quality Fellow, again at Kolkata, so she is also related to West Bengal. Yeah. AGU Thriving Earth Exchange Community Service Fellow for Ohio, and sits on the Bay Area Air Quality Management District Advisory Council. She holds a BA in data science and a BS in civil and environmental engineering from the University of California, Berkeley. She is a recipient of the Women in Science Incentive Prize, Health Effects Institute Jane Warren Award, and National Science Foundation Graduate Research Fellowship. Garima has formerly worked at the
Hi everyone, excited to be here. I'm just thinking that if I'm gonna spend this whole conference talking after Samya, then clearly I need to rename my project to Chutney or Pakora or something. So if anyone has ideas on renaming this project, getting that acronym, please help me out. But in the meantime, this is going to be about the idea of correcting maybe 20,000 low-cost sensors that are deployed all around the world without a co-location. So we're developing a global Gaussian mixture regression model for optical PM2.5 sensors. And my contact information is here. It'll be at the end of the slides as well if you want to chat about it later. So this is what we want, right? This is what we all want. We want a reference grade monitor in, the exact site that we want to measure. This is a site from New York City that's right next to a roadway. And we know that the cost of these monitors and the associated, transportation, climate control that go with that is in the range of the US dollars 100,000. This is what we get from a low-cost sensor. It sometimes matches up, sometimes not very well, but the cost is in the range of, 250 US dollars, which is great. What we've traditionally been doing is co-locating a low-cost sensor with a reference monitor so that, the cost of that becomes 100,000 US dollars plus the 250-ish dollars of that low-cost sensor. And the mean absolute error we've come to expect from something like this is 2.67 micrograms per meter cubed or something in that range, right? So this is the cost that we're looking at from a traditional co-location. What if I said you could have this, this level of accuracy, 2.99 micrograms per meter cubed, so that'd be a low-cost sensor plus something else. How much would you be willing to pay for this?
Garima loves to be interactive, so please go ahead and say a number, otherwise she won't proceed.
Okay, 10 grand, 10, 20 grand, thank you so much. That's why we're introducing the global Gaussian mixture regression correction model, the idea that you could get something of that accuracy for theoretically free. So I'll talk a little bit about the motivation. I'll talk about how we're getting the data and comparing the correction factors between different cities to assess the validity of this model, and then developing the global model and what's coming after that. So the motivation, as we know, this is a graph that I think a lot of you have seen, or you could probably make if you had to just out of memory, is that the amount of air pollution is disproportionately distributed around the world, but then so is also the monitoring infrastructure inversely correlated with the pollution levels around the world. This is especially a big problem in Africa and South Asia, and so we want to make sure we focus on those regions. Traditional monitoring is expensive, so you take the instrument, you take the assembly and maintenance, you fly people around the world to install them, you put climate control, the cost becomes unreasonable for a lot of places in the world. So the solution recently has been low-cost sensors, which you all know about. And with the low-cost sensors, the corrected low-cost sensor data can be pretty good if you apply the right data science methods to it. But how do we get this correction factor is the question. So we co-locate with a reference monitor. If you look at the distribution of reference monitors around the world, this is what that looks like. And you add the low-cost sensors around the world, there's a lot more of them. So wherever you can do those co-locations and in the regions right around those, we can have corrected data from these co-locations. But what happens to all of the different low-cost sensors that don't have a co-location nearby? Are they data that we can even use, or do we just have to, throw them out? So let's take this idea of a distribution of PM2.5 from one city. For example, let's say Accra, Ghana. This is the distribution of PM2.5. This is the data point that we want to correct. Do we have a lot of data at this specific data point from this distribution? No, I see heads showing no. But if we added the data from Delhi, then we have a little bit more data at that one data point. And then what if we also added, something from Indonesia? Then suddenly this training data set that we've created has a lot more data at that one data point that we wanted to train on. So we can have theoretically more confidence in the result that comes from that. So all of these different collocations and all of the areas that don't have a collocation, you could theoretically create a model that could also help that by using this global training data set. That's what CAMS-Net has been really useful for, so thanks to everyone who's been contributing through this network of networks in the collecting, the cleaning, and the development of this model. Integrating data from all these sources has been really important. The reason that we are using specifically a Gaussian mixture regression model is that it's very good at identifying regimes. So the humidity and temperature regime in one part of Africa might be very different from the regime in northern Japan. And so this is a model that is adept at classifying and then training your, creating a regression that understands that different places might have different regimes. This is what the global collocation data set looks like right now. I apologize, this is pretty fresh, so it might be a little rough around the edges. The map on the corner shows the collocations we've been able to integrate. There's still pretty big data gaps, but if you look at the huge scatter plot on the right, it shows you all of the different sites. And the shape of the dot tells you which kind of low-cost sensor we're integrating data from. So maybe that scatter plot is too much, so let me show you some distributions to show what kind of data we're looking at. These are the low-cost sensor reference temperature and humidity distributions. The y-axis is 10,000 to give you a sense of the amount of data that we're putting into this model. Again, thank you to everyone who has contributed collocation data. If you have data, please get in touch with me. We can definitely integrate that into the next version of this model, and I think the more data we have, the better this model could be. So the first thing I wanted to compare was how can you apply a correction factor from one city to another, right? Could we just take a correction factor from a random place in the world and put it somewhere else? I think most people in this room know that the answer is no, but to quantify how much that is, we use this pretty large data set of about 40 collocations to understand how much that actually matters. So the way that we're doing this is, I'm going to show you a graph, but before I show you the graph, I'm going to explain what the graph will show. On the y-axis, it will be the city that we train the model on. So that's the 40-ish cities that we're assessing. And on the x-axis will be the city that we're testing on. So we train the model on one city. We calculate the mean absolute error of the model on that city itself, on its own data. Then we test the model on a new city, and then we find the mean absolute error on that new city. And then what the graph colors will show you is the one divided by the other. So if the number is really high, that means that the mean absolute error magnified a lot, and if the color is very light, that means the mean absolute error didn't change very much. Understood? Okay. So this is a lot of information, but the key trends I want to demonstrate from this are that sometimes training a correction on one city and applying it to another works very well. So in these areas I've highlighted in green, the mean absolute error only magnified by 1 to 2 times. So if you maybe went from a mean absolute error of 2 micrograms to 4 micrograms without actually putting a collocation in that city. So this is essentially free, right? So that's pretty impressive, and you can see that pretty large parts of this graph are pretty light colored, below 5x magnification of mean absolute error. So I think that's very promising. Of course, other times you'll see these big red lines, which means that there's a really high magnification of the mean absolute error. Some of these numbers go up as as high as 20 to 40 times. You might wonder why that is. And as Samya talked about yesterday, it's all dependent on the data that you put into a model. If you put in good data, you get good stuff out. If you put in not so good data, you might not get something as good out. So the second line we're looking at the bottom is from Nairobi. And one of the reasons that it's all very dark red is that the collocation itself didn't have a lot of data. So you train a model on not a lot of data. You don't have a lot of range in the PM2.5 or other characteristics. So of course, when you try testing it on other cities, you're not going to get great results. So the model is better than the sum of its parts, but the parts have to be good for the model to be good as well. So I'm going to pause and ask if there's, actually we're not doing questions, never mind. We're going to talk about developing a global model. So as I mentioned, using the network of networks in CAMS-Net, we've been aggregating co-location data from all around the world as much as possible, putting it into this massive data set that will also be available, when this is published, so you can also train your models on this data and make one better than this one, please. Applying a global Gaussian mixture regression machine learning technique onto it. If you want to learn more about that technique, you can read a paper by a wonderful undergrad in our group, Celeste McFarlane. I'm not going to go into details about that. It's pretty technical, so you can read about it later. And then the results I think I want to focus on are something like this. So we have a lot of graphs here. I'll explain. The graph on top shows all of the different collocations and the mean absolute error from a local model that's just trained on that city in blue. And then in red is the mean absolute error from using a global model that does not include that city on that city. So if the blue line is high, that means even the local model creates a high mean absolute error. If the red is high, it means that the global model also creates a mean absolute error that's very high. So that's the top graph. It shows two different values. And the bottom graph just shows the division of those values. So the global divided by the local, so the magnification as we were talking about previously. And what I want to identify is that for most of these collocations, the magnification is less than 2. So by using a global model that doesn't even include that city, it's essentially free because you don't have to put a reference monitor in the $100,000 range. You're just using a model that's freely available based on everyone else's contributions. The mean absolute error you're getting is only twice as bad as the mean absolute error you would have gotten if you just used a local model. Obviously, it's not as good, but just remember the fact that it's free, like you didn't need a reference monitor. So in most cases, it performs almost as well, which means it's very useful for cases where you cannot do a local collocation because of funds or availability or whatever. Of course, it depends on the data quality and the length, as well as the number of components you pick within the model. So you have to put good data in to get good models out. But I think this is still very promising, and I think this is going to be very useful for a lot of places in the world that cannot afford to put a reference monitor. As we talked about, cost is relative. Even a low-cost monitor, is expensive enough for a lot of places in the world. So we want to make sure that we're creating things that are useful for those very burdened communities in Africa and Asia that really need these. So in the end, what happens is that using this global model, all of the uncollocated sensors previously can turn into corrected low-cost sensor data. So this is the idea of the 20,000 monitors, low-cost sensors that are deployed around the world. Theoretically, we could use this model to get something meaningful and data from them that is corrected. This corrected, high-quality data can lead to a lot of, I think, important research that can come out of it. The research, you can do high spatial resolution exposure research, comparing it to demographics, climate migration, heat, redlining, and other concepts. You can also integrate this data with mobile monitoring or models or satellite measurement because this will have such a high spatial resolution. There is an undergrad in our group who is focusing on redlining, so I hope to be able to show you that results soon as well. But this is an urban policy in the United States that's really deeply correlated with race and income. And so it's been interesting to see the results from correlating that with high spatial air pollution data. So in conclusion, there's a lot of next steps. There's the possibility of using other machine learning models. There's also more features of data you can add. There's more cities, but there's a question of which cities would be useful to add to this model. And the goal is to create an online tool that everyone can use. So hopefully the test version of this will be out pretty soon, where you can just plug in your low-cost sensor and get corrected data out using a global model without having to do the training yourself, which is computationally intensive. The key takeaways are that the global model can be used when local collocations are not available. You can use, I feel like my estimates of how many low-cost sensors have changed in all these slides because at different points there were different amounts. Theoretically, you could use this model to correct data from the thousands of sensors that are deployed around the world without a collocation, which could really increase the data availability in places that are most impacted. Global GMR is better than the sum of its parts, but the parts have to be good for it to work. And finally, this model shows a lot of promise, but there's a lot left to do, so the data will be out for everyone to be able to experiment with it as well. Thanks to everybody who has helped with this project. There's way too many names to fit on this slide, and a lot of you are in this room, so thanks for all your help.
Thanks, Garima. Our next speaker is Dr. Kofi Amega, who is an associate professor of environmental and nutritional epidemiology in the Department of Biomedical Sciences, University of Cape Coast, Ghana. He leads the Breathe Accra project, which seeks to accelerate air quality improvements in the Greater Accra metropolitan area to protect public health and help inspire greater action on air pollution in other African cities. He also leads the Ghana Urban Air Quality Project, which began in 2019 and anchors the Breathe Accra project. He is a founding member of the Afric Air Network and a collaborator on the Global Burden of Disease Studies. One more thing I would like to add here that was not mentioned in his bio that was shared with me is he is also one of the deputy editors of the Journal of Health and Pollution. So, okay. Over to Dr. Kofi.
Thank you for the very kind introduction. And a good morning to you all, and greetings from Accra, and then also Cape Coast, where I am based. I'm very excited to be here this morning and to speak to you about this project, which is generously funded by Clean Air Fund. So this is one of the earliest papers that myself and a colleague at the University of Ghana wrote, and we started to document the air pollution problems in Africa and also started to propose some solutions. And one of the solutions was to step up monitoring on the continent, where we have very limited ground monitoring instrumentation. I think earlier this morning, Dr. Faye showed this map, which was for 2019. I've updated it. This is from the 2024 map. The issue with here is that in Africa, where we have very limited ground monitoring, what you see here is mainly coming from satellite data. And many in this room who are aerosol scientists, atmospheric scientists, knows the shortcomings of satellite AODs. This is household air pollution, which is also a major problem on the continent, and importantly, is also a major contributor of ambient air pollution levels in Africa. And this emanates, for the uninitiated, this emanates from burning of charcoal and wood in the household for cooking and then also heating. And again, in the SOGA report, we start to see that now air pollution has overtaken tobacco and then also diet. Tobacco and diet are very important risk factors for health. And so if we have air pollution overtaking them and just behind high blood pressure, then it means there's a cause for action. And it means we need to step up our game to try and clean the air so that we can protect public health in our neighborhoods. It's also impacting children mostly, who are the most vulnerable groups. And here you see about 709,000 children were impacted by air pollution. And in Africa, this is more of a problem because especially in the household, mothers are cooking, they don't have nannies who are taking care of their children, so they have to carry them on their backs and do the cooking, and they are exposed to this high level of pollutant, which impacts their respiratory health. So on this background, then we started to sit with Clean Air Fund to initiate this Breathe Accra project. The context is, as it is in many jurisdictions, low-income jurisdictions. There is a growing problem, air pollution problem in Accra. City authorities are not acting on it for several reasons. One is lack of capacity, one is lack of investment from government. Accra has an air quality monitoring program which is run centrally by Ghana EPA, but there are opportunities. You know, there's a very nice decentralization systems, and they have environmental health department. So we thought that we could leverage these opportunities to enhance the monitoring network and also get them to be actively involved in the monitoring program in Accra. Let me indicate that I'm an epidemiologist, and one of the undocumented quests for setting up, or motivation for setting up this project, is the quest for exposure data. So again, what we are doing is that the data that we are gathering from here, we are combining with outcomes data to try and also generate some health effects, air pollution health effect estimate to input into the global burden of diseases studies. So this is, the Ghana Urban Air Quality anchors this project. The vision is to accelerate air quality improvement in Accra, but also to serve as a blueprint for other countries in Africa to copy, replicate, and then we have a very nice story on the continent. Let me go back. The objectives are threefold. We hyperlocal air quality data in Accra. We have a very nice website which documents all the data. We've done a number of trainings for these people in the environmental health department who are supporting the project, and then also we want to share the details. So the four main pillars is, as I indicated, I'm an epidemiologist, so we are interested in health effect studies. We have built capacity on the project. We are doing stakeholder and community engagement where we are interfacing communities with the data. And then we are also doing risk communication using volunteers. These are some of the sensors. Clarity, ECHO, which is, I like ECHO, is developed on the continent by the folks in Uganda. We are using AirNote, and then we are also deploying some IQ Air. Site selection is based on the community structures. So we have sensors in schools, in hospitals, in market centers, in lorry stations, waste disposal sites, and then also residential neighborhoods of varying socioeconomic status. We have some TIOMs that were donated by the UK Monitoring Agency together with Subu and others, Mike here. We had about 10 in Accra. We've been able to deploy about 4 or 5, but I must indicate they are giving us challenges, because they are very obsolete equipment. But in an environment where you have none, you have to be grateful for whatever you get. These are some of our clarity. That is our data architecture, and I came to this meeting with our data manager who has a very nice poster. And so we fetch the data, we clean, and then we analyze. So this is a Brit Accra website. So we have deployed over 65 sensors in Accra. We are working in, originally we started with 13 districts, beneficiary districts, but I'm happy to report that we've started roping up other districts. So just recently we added another district which stretches the measurement, the sensors to the west side of Accra. We are planning to go to that side as well very shortly. And this is the Ghana Urban Air Quality Project, which gave birth to the Brit Accra project and which anchors it strongly. And this we started in 2019 with help from some folks in Colombia, Dabijak, Subu. They gave us sensors. I was also buying sensors from my packet. And the objective here is to ensure that we have sensors across all metropolitan areas in Ghana. Our sensor in the north is one of the very first air pollution measurement that we are taking in northern Ghana. The red dot that you see there is all the sensors in Accra. You click, it opens up the Breathe Accra website. One thing I want to mention is that you can go on this website, click on air quality at location, it scans for your location, and it gives you in real time the air quality levels in the location where you find yourself or you are domiciled. That is our data analysis plan. I won't waste time. Most of you in this room are familiar with these methods. But to indicate, though, this is how we visualize the data on our website. So we have the heat maps, and all this is done nicely by the young gentleman, Patrick, whom you will see behind his poster. So each month he downloads all the data, that's the averages, that's the heat maps, and projects them on the map. And then we also have a slider. We have the time series, and it's a slider, so you can slide and know air pollution maps at each time t. So this is time series for the NO2, and then also, and then what we've also been trying to do is that we are trying to dig deep into the data that we have. So these are some locations where we have clarity, and We have major rainy season measurement, harmattan season. What we are seeing and baffles us is that there are peaks both in the rainy seasons and in the harmattan season. And we are expecting that in the rainy seasons, the rainfall is going to douse these measurements and they're going to be low. So these are things we want to explore to try to understand what is the what is behind these things that we are seeing. These are heat maps that more or less corroborate what I just showed, and it's also showing the same high measurement in the rainy season and the harmattan season. So how do we use the data? We, earlier on in the presentation by Dr. Fay, she highlighted the promises of these low-cost sensors. And one of the things we are doing is what she mentioned. We are using the data to identify air pollution hotspots so that we can interface with the communities, interface with the districts, and then be able to put in some interventions to mitigate air pollution in those locations. We are also using the data to promote local action, behavioral change. So we are on radios, we are hitting the streets, we are writing articles in print media, we are very active on social media, making noise, and we are trying to create some awareness about the air pollution problem in Accra and beyond Accra so that people can change their ways of doing things that is polluting the space, and we can have clean air in our space. We are also doing risk communication, and we are leveraging on volunteers from our university and also in Accra. Recently, we're part of the Air Quality Awareness Week, and we had about 60 volunteers in the space of Accra doing awareness creation in the landscape among vulnerable groups like street vendors, like waste pickers, like traffic policemen. We are also informing policy with the data, and recently we had an assembly of all policymakers in one of the hotels in Accra, where we try to come out with a communique on how we can address the air pollution problems in Accra. And on the air pollution hotspots, so this is a map that again was generated by the young gentleman there, and here you see neighborhoods where we have identified as hotspots, and we have started to put in an intervention. But in the interim, you cannot go to assemblies and tell them to, for example, buy electric buses. You cannot go to assemblies and tell them to, for example, start developing road networks with sidewalks so people can walk. So what we did quickly was that we developed this intervention, this sensitization manual, which we have published on both websites, and we have printed them, giving them to the environmental health officers, and they are using them to do sensitizations in the communities to change behavioral and attitude for us to have clean air in the neighborhoods. Just to end, we are also trying to look at the data and trying to get some publications. So this is a paper that we have just submitted, led by Patrick, and on utility of low-cost sensor measurement, where he tried to compare it with satellite AODs using a number of machine learning techniques. I don't want to take the wind out of his sail, so the poster is out there. You can meet him and learn the methods that we have deployed on this application, on this thing. So in conclusion, it's imperative to generate air quality data to drive policy decisions and inform public awareness. This obviously will help to protect public health, and I'm a public health practitioner, so of course, that is my motivation. Low-cost sensor technology should be leveraged to bridge the huge data gaps in Africa. Sensors should be co-located with reference monitors to inspire confidence and trust in the data. And I'm happy that people like Alison, Indiset, etc. have this evaluation center where we can take sensors there for evaluation and have the most promising ones to deploy. So that is what the last point takes about. The most promising sensors should be embraced to assure data quality and inspire greater confidence in the decisions that are rich with the data. We cannot do this without the support of the partners. So I acknowledge them, Clean Air Fund, who gives us the money, the Bridge Cities Initiative, which we are part of, Ghana Environmental Protection Agency, Clarity, etc. We are also working with Ghana Health Service. And these are our websites. You can visit them to see the nice things we are doing there. I'm active on social media and my email address. Thank you very much.
Thank you, Dr. Kofi. Our last speaker is Dr. Prabhat Kumar Shah. He will be joining us virtually. He is a research scientist at the University of Washington in Seattle. He earned his PhD in environmental engineering from North Carolina State University and did his postdoctoral training at Carnegie Mellon University. Dr. Saha has applied his expertise in air pollution projects both in the US and Bangladesh. Is he joining like live or it's a pre-recorded talk? Pre-recorded. Okay, so we will listen to his pre-recorded talk.
I'm giving my talk from USA virtually. I would like to thank the conference organizing committee for giving me the opportunity of this virtual talk. Let's share my slide deck and go to my presentation. All right. The title of my presentation is Characterizing Fine Particulate Air Pollution in Rural Areas of Bangladesh Using a Network of Local Sensor. I like to acknowledge the contribution of my co-authors listed here. The key motivation of this work is in the rural area of Bangladesh, we know very little about the PM2.5 pollution level because there is almost no measurement exist. Bangladesh is often highlighted for its bad air pollution, and about 2/3 of population lives in rural area, but we know very little about the rural pollution levels. There are a couple of continuous air monitoring stations exist in Bangladesh. Currently these are 15, and this map shows the location of these continuous air monitoring stations, but all these locations are in heavily urbanized or in big cities. So there is no monitoring station in this local rural area since the traditional air measurement is very expensive. So our motivation here is can you utilize low-cost sensor to understand PM2.5 pollutions in rural Bangladesh. With that motivation, the specific focus of this talk is first evaluate the performance of low-cost sensors. In our case, we use the popular sensors, and then characterizing PM2.5 levels in rural Bangladesh using a network of low-cost sensors. For this, the calibration part, we did the collocation of 20 popular sensors at a continuous air monitoring station in Dhaka. This is a photo from this collocation where we had bunch of sensor close to a Mate-1 BAM. That's our reference monitor, and we collected collocation data in 2 seasons. Each season 1 month of data collection, 1 month in dry season and 1 month in wet season. This trace shows one example of this the collocation data. Here this black trace shows this the data from this BAM, this DOE PM2.5 monitor, and different other color trace shows the data from individual popular sensor. You see there is excellent, these are the popular data as measured with CF-ATM. Popular report PM2.5 using 2 different calibration factor, internal calibration factor. One is the CF-ATM and another is the CF1. This is with the CF-ATM. And you see there is excellent consistency for this the measurement from different sensors, and as measured CF-ATM1 is kindly aligned with this the BAM data. To get this further accuracy, we develop calibration model using collocation data set. In our cases, we try different statistical modeling form. The simplest one is linear one, and then other one is a bunch of multiple linear regression. We also did machine learning using this random forest model. This is very visitable, but main takeaway is different models that's model form we tried, and the main takeaway here is in terms of this normalized RMSE, the accuracy we got between 12 to 20%. For this, the machine learning, it's around 12%, and for this linear and MLR models is varies between around 16 to 17%. So this is, I think, for hourly PM2.5, and it's not bad. And to summarize this, some of our lessons from our collocation, if we use this as measured CFATM, we can get around 20 to 25 percent error, but CF1 that's sometimes can give high error. And if we do the different correction model, it helps a little bit, and we can get the error within 12 to 20%. So that's our correction models can help a little bit. We also check the transferability of other models that's developed in different locations, for example, in Indian cities, also in US cities. But transferability of this location for Dhaka specific conditions or Bangladesh specific condition was not that great. So we need basically the local model to get the higher accuracy. And with that, I would move to now the sensor deployment in various rural locations. This part, so this map shows the location where we deployed the sensor. These are the different rural locations across this country. We had 20 locations, and this is some of the photos from rural deployment side. You see the sensors here in some residential locations, and this is another one. And these locations are distributed across this country, and so far we collected data across multiple seasons. In the dry month, we have four months of data. In the wet month, we have 4 months of data. So we have a good data set to talk about. Since we use the same set of sensor for both collocations, calibration, and the rural deployment, how we did this, the data collection, first we did the collocation at a campsite in Dhaka and collected 1 month of that data in the wet season, and then we deployed those sensors in different rural sites and collected about 4 months of data, and same things we did during this dry season, about 1 month of collocation data where we kind of put all the sensors together in the campsite, and then after that we put them in different field sites. Going into some of this result, to present this result, what we did here, we grouped these sites into different regions: eastern, some part of the country, central part, and this western part. And we also compare our measurement with 2 campsites within this Dhaka city. This is the results. PM2.5 average across 2 seasons. So this is kind of annual average PM2.5. And what we see in terms of this pollution level, it varies between 60 to 120 microgram per meter cube. So its level is high, and on overall we see the eastern side has a little slightly lower pollution level compared to some of the western part of this country. And if we compare this data from 2 campsite in Dhaka, that's located in the center part of this country, right? And these levels are kind of comparable with many rural locations you see. So one question is, how rural are the measurement sites? We compare different land use related parameters with the urban sites and this rural site. This is like population density around sites in Dhaka compared to the rural sites in different locations. You see those sites has this very low population density. A similar thing for this non-agricultural enterprise. This site has this low non-agricultural enterprise density, and for the same thing for this road density, and this is like distance to highway or primary road. Those locations are rural locations are pretty far from the highway or primary road. So these sites are pretty rural. Then come into the seasonality, we see very strong seasonal difference between across all sites. In all sites, in the dry season, concentration are much higher, including this urban site, but in the wet season, it's much lower. That's the kind of typical trend in PM2.5 pollution in Bangladesh. Then we compared this measurement with also satellite measurement, satellite AOD. And these are the satellite EOD data around 5 kilometer buffer distance from each of these sites. And what we see, we kind of see the similar trend as the ground measurement. There is some east-west different, and when we compare with the Dhaka city, it's kind of similar, like pollution levels are kind of regionally distributed. Seasonal difference for this aerosol optical depth or satellite EOD, like ground measurement, we see much seasonal difference, but with the satellite EOD, the trend is similar, but in terms of magnitude, we see the difference is a bit lower. The seasonal difference is a bit lower. In our previous slides, we just compared this rural measurement with the measurement from two urban sites that's located within the city center. This slide is comparing the available data from different other urban sites that's operated by DOE, and we kind of see the similar trend, like eastern side in both urban sites and rural sites has a relatively lower concentration compared to the western sites. And there is no significant difference between this urban and rural. AOD gives the kind of similar conclusion. So main takeaway here is many people in Bangladesh or policymakers, they think the air pollution is basically urban things and rural area is pretty clean, but our data set, both ground measurement and satellite data, suggests that rural areas in Bangladesh has this PM2.5 pollution levels that's comparable to urban areas. Sometimes it's lower, but it's not clean rural. And here we use this local sensors, so and locally calibrated local sensors can provide valuable insights and can affordable air quality measurements. Here we acknowledge funding from different sources, Rise, Good, and Open Philanthropy for this the work. And if you have any questions, please email me at my email address that's given here. And thanks for your patience, and thank you.
Before I open the floor to questions, participants who are joining us online, please feel free to write your questions in the chat box, and we can address them. Okay, so the floor is open to questions. Feel free.
Hello. I am Mangi Mehta, and I am a PhD student from IIT Bombay. I would like to ask a question to Ms. Garima. So when you showed the result for mean absolute error, it was not showing good for Chennai as well as DEL Delhi, which I suppose. So, and also for some of the African countries. So is it, one of the reason was missing data, but in Delhi, I suppose there are a lot of sensors and data is available. So is it because of the levels of the pollution are much higher as compared to the European or US countries where you have calibrated it or done the measurements? And another reason can be the meteorology. So can it be improved by integrating the IMD data, that is Indian Meteorological Department data, or some local weather stations data which are more easily available than the PM sensors or other sensors? So your comments on that.
Yeah, that's a great question. Thank you for noticing. I only showed, the reason for Nairobi instead of going into all the reasons for all of the other, data quality. Yeah, definitely. I think it could be improved by adding data from meteorological agencies. I think it's just important in creating, a global model to make sure that the data that's coming in is standard. So a lot of the work for developing this model has been like data cleaning and data standardization. And every country, every meteorological agency reports their data differently, and some countries and some regions have that infrastructure to have that data and have it be very high quality, but a lot of the regions that, the data here is coming from don't have that kind of infrastructure. So I think for now, the data that's been integrated into the model is purely just the data that's coming out of the low-cost sensors. And of course, you can add so many other data inputs, data features into that to make it better. But I think for version 1, the goal is to just use the data that's coming from every single low-cost sensor.
Okay. Thank you.
Thank you for this wonderful session. My question is to Dr. Soumya.
If you could introduce yourself,
Oh,
please.
sorry, yeah. I'm Tarusha and I'm from Aizer Mohali. Actually, the pictures in your presentation really intrigued my interest as a social scientist. I would like to know a little bit more about how the location of the sensors is determined on the field. And I think we did discuss about it in the yesterday's session also. My question is, are there any social, demographical or cultural considerations when we are putting sensors up? And especially when we are talking about small cities or villages. And the second question is whether we need some sort of government permissions or maybe a formal or informal intimation to the local governance officers when such projects are undertaken. Thank you.
Yeah, am I audible? Yeah, I think. Thank you for your question. Great question from the social scientist. Always hard to answer. So for the first part, I would say when we were deploying sensors in villages, we were definitely considering, because in cities, I mean, on record or we don't have documentation that how culturally or for the population spread in village or city, how we will go and deploy the sensors. But when you think about the city versus village in India, I'll bring the caste and the cultural part of it. So the city, I don't think we have that kind of divide. We do see slum area in between. So our goal was to definitely cover that, but because of the logistical reason, we couldn't achieve that. In villages, we were putting sensors, covering all the, so for example, in a village, we will go with the limit of, 4 sensors we have. We limited ourselves for the 4 sensors. So, because of the population density is also low in villages. So, we definitely mapped all caste and, the classes, but it's not something, maybe, at least it was in mind, but it was not really the base for our deployment, And the second part is something we can chat later. I think, yeah, it's bit, yeah, I do not have answers, so I'll be happy to chat later. Thank you.
Yes, go ahead. Introduce yourself and...
Hello everyone, I am Amita Devkate from the Aeron System Pune. My question is to the Dr. Soumya, that we are validating our low-cost sensors with the reference grade monitors. Well, but how frequently you are calibrating your reference grade system? Why I am asking this question to you? Because we are already validating our sensor, our Aeron devices with the reference devices, and when we exposed these reference grade devices, 2 or 3 reference grade devices in the Pune city, so we find a lot of the data gap. So how to overcome, and how confident we are that these reference grade devices are showing the 100% accuracy?
Thank you for, again, great question. So if I understand your question, you're asking how do we ensure that the data gap is coming from the reference grade monitor, not the low cost sensor, right?
Yes.
Yeah. So for us in our project, the reference grade monitor was not, which is regulated by government agencies. So we had our own BAM in different co-location sites. So we were very much maintaining and, maintaining that monitor. So BAM was the reference grade monitor we were using. But yes, you are absolutely right. Like when we are using anything which is, city network, which is already, governed by or regulated by any government agency, or, so it's, the control is not really on the user side, right? You would not have the control for the data coverage. There are different reasons, could be data missing. So how to compensate that? buy your own BAM. Sorry, that's a bad joke because we cannot. But then what do we do? I think whatever data we have, we can just try to get that, we can come up with some kind of our own metric, not metric, maybe, if that, for example, if a site, if a reference grade monitor have a coverage across, all over, covering all the seasons, just come up with some, your own criteria that if that, site has coverage of 50% of that season. So you really have to look at the data. I don't know if I answered your question.
But my point is actually you should display the calibration results, like whatever you are following the method for calibration of the reference grade, like you are passing the known concentration of the gas or the zero gas calibration. So in previous session also that session is on the low cost sensors validation data with the reference grade. But I find this point that you should display present the calibration results too, so that we can confident that this much data gap is there, or like a known concentration is this much, and our reference grade device showing this much results. So we can
right. So you're saying about the comparison of low cost sensor and reference.
Yes.
We can chat more, after this, but we do, I think most of the presentations are showing that, that 20% or 30%, so yeah. Okay. So we can discuss later.
Yeah.
Thank you.
Thank you.
Is there a question from the online?
So hi, I'm Neerav Lekinwala. I work at CSTEP as a senior associate, and I have a question for Garima. So the model that you built, you have some reference monitors, and you have the low-cost sensors located, which may be about more than 100 kilometers or more apart. So you're using the reference rate monitors data and calibrating the low-cost sensors. But how confident are you in the data for low-cost sensors? I'm not talking about the reference rate. And will the data that you've used to train the model, will that affect when you're predicting it for some other sensors? Let's say if I upload some data on your website, as you said, you have a version coming up, and the predictions, how well will it match as compared to the? I hope you get my questions right.
Okay, so I think I understood two questions now. The first one was, how much do you trust the low-cost sensor data? And then the second one was, how good will the predictions be? I think both of those are, so how much we trust the low-cost sensor data, that's some of the first graphs that I showed, the training on one city and testing on the other city. That's what we're trying to assess. The cities where if you train on one city and you test it on itself and that performs well, that's like the first step of assessing if it's good. Then training on one city and testing on a different city, that's another way to see if it's good. That's how you can identify the Nairobi data set not being very good. So it depends for each co-location how much we trust the low-cost sensor data, and there's a lot of analysis that goes into figuring that out. And then how good the predictions are. Again, I think the way to do that is to test it on itself first to see the quality of the data in itself, and then test it on other cities to see how well it performs when you transfer it. So yeah, the answer is it depends on every city, and there's figures to help understand that.
Okay.
Hey, so I think one thing for me, and I've been working with sensors for like a few years now, more than I care to imagine, but I think a lot of the questions so far have been on calibration models and correction factors and all that, right? And I mean, I really like Kofi's approach, right? Like, oh, we did processing and it's fine, and we're moving on to what we really want to do, because at the end of the day, we really want to use the data for something useful, to improve air quality, to reduce health impacts. So from that perspective, I mean, probably starting with Kofi, but Garima and Soumya can also answer, how do you see this data being used? I mean, do you really need neighborhood scale data? I mean, one question is, do you need that? I think there are some points in Kofi's data that some NO2 levels were higher than others, but in general, I mean, if you're looking at, say, hyperlocal measurements or even rural areas, I mean, Soumya did it in the IGP, do you really think we need that many sensors, or do we need 100 sensors in a city, and what can that data be used for? I'd like each of you to maybe say something about it. Thanks.
Yeah, from an epidemiological standpoint, we need thousands of sensors. Yeah, so that we can have granularity in the data, you know. But in terms of using it to inform policy and also for public awareness, I don't think we need as many sensors as we have deployed, you know. Because, for example, if you look at the developed countries, they have the reference monitors. How many do they have in each particular location? So that is my answer. Again, the other part of your submission was the approach that we're using. I mean, there's a lot of emphasis on calibrations, correction factors. But I also strongly believe that in an environment where we don't have anything, any indicative measurement is good to advise the public as to what the levels of pollution are so that they can advise themselves. But I must also indicate that we need to also get to a point where we need to inspire confidence in the data that we are producing. So again, through the generous funding from Clean Air Fund, we've managed to secure a BAM, which you are aware. And the next phase of the project is that we want to try and correct all the data before we upload on the website. So any data that you see on our website are corrected data, because I guess that is the direction we want to go. Yeah. Thank you.
Thank you, Kofi. And before we move on to one last question from this floor, I would like to confirm that if there is any online question from the chat box. No. So, yeah, one last question. After that, we can carry on the discussion during the lunch.
Victoria again. This is to Kofi, but not a question, a suggestion. I don't know how far or the extent your work has gone with regards to meteorology. There was a point you made on one of the plots where there were peaks, recording peak levels in July, and then you said it was surprising. So I don't know the extent to which you factor in meteorology in the initiative that you are working on. Mostly in July, August, the monsoon starts in April. In July, it reduces, and so we get a lesser dry season. So meteorology could be playing a role in that peak levels recorded within that period. So if you would consider that in your analysis, I think it would be good.
Yeah, thank you, Victoria, for that point. And I think the paper that Patrick is leading is we considered, we accounted for meteorological information and also spatial information in the analysis. But as I indicated, we are trying to dig deep into why we are seeing these peaks during a period where we should have lower peaks. And from your background, maybe we can collaborate with you to assist us to understand some of these things. Thank you very much.
So thank you to our speakers for your excellent talks, and thank you to the audience for participating. We are wrapping this up.